So far, we've been studying linear regression, or the line of best fit, through some data. And we came up with some formulas that tell us, here's a formula for B0, the intercept of the line of best fit, and here's a formula for B1, the slope of the line of best fit. Now, whenever we come up with a formula like that, you should be wondering, how much uncertainty is there in those values? That is, do we know that the true intercept and slope are exactly what the formula says? Or maybe we're not quite sure and there's some uncertainty. And maybe we've got the data world values of the intercept and slope, but maybe there are some underlying theoretical values from the theoretical world, and there might be some uncertainty about them. So let's consider that. To set it up, let's first of all concentrate on the slope, because that's usually more important. And we have a formula for the B1, the regression slope that we get from the data. And the question, as I said, is what's the uncertainty? Can we get confidence intervals? Can we do hypothesis testing for the true value of the slope? So for this to make sense, we have to imagine that there's a theoretical world with a true underlying slope, which we'll now call a beta 1 to distinguish it from the B1, which is the experimental or a data world. And now we want to say, how close are these things to each other? That is, we got from our data in that formula, we got a data world value B1. How close is that to the true theoretical underlying value beta 1? Well, there's a very important fact that we're not going to justify here, but it says that this coefficient for the slope, it also satisfies a sort of a t-distribution. And indeed, if you look at the experimental value B1 minus the true theoretical value beta 1 and divide by a certain standard error of B1 that we'll talk about in a sec, then that also has a t-distribution, kind of like those confidence intervals and hypothesis tests that we did before. In this case, it's a t-distribution with n-2 degrees of freedom. We kind of lose 1 degree because we don't know the slope and lose another degree because we don't know the intercept. Anyway, it's just a fact for us that this formula has a t-distribution with n-2 degrees of freedom. And that standard error involved, well, that's a very important quantity for doing things like confidence intervals and hypothesis tests. And it turns out to be given by this crazy formula here. So the square root of the sum of the residual values, EI squared, divided by a square root of n-2, that same number of degrees of freedom, times the sum of the xi's minus their mean squared. So this is the formula that we're going to use. Once we have this fact, or we have this formula, then we can say, well, we can do things like get confidence intervals, and it's really the same as before. So we'd set it up and we'd say that now if we want a confidence interval, say to cover 1 minus alpha of the probability, well, that would be just kind of like it was when we had confidence intervals using the t-distribution before, namely the observed value, the B1, plus or minus the appropriate critical value, t sub alpha over 2, comma n-2, because there's n-2 degrees of freedom, times this standard error of B1. Well, that's that crazy formula from the previous slide. So now we can say, well, let's do that skeletons example again. So that example of a regression that we had from the previous lecture. And there, remember, y was the age differences, the difference of the estimated minus the actual age of the skeleton at death. And x was now the BMI, the body mass index. And we had this data for 400 skeletons. And then we can say, well, in the experimental world or the data world, we computed a slope which was equal to B1, and it was plus 0.41. Then we compute, first of all, if we're going to compute that standard error thing, we have to compute the sum of the EI squareds, and that you can just compute or get a computer to compute it. It worked out to 78,132. We also have to compute the sum of those squared deviations of xi minus x bar, and that worked out to 8,992. And also we need that critical value for the t-distribution. Well, since it's a large number of degrees of freedom, it's probably pretty close to that usual 1.96 for the normal. And in this case, it's actually 1.97, just a little bit higher. And then we can get the confidence interval the same as before. We take the observed value, the plus 0.41, and then plus or minus, well, that critical value, 1.97, times the square root of the sum of the EI squareds, divided by the square root of n-2 times the sum of the xi minus x bar squareds. And when you work that all out, it works out to an interval of between 0.12 and 0.70. So now we can say that when you're comparing the age difference for the skeletons compared to the BMI, or the body mass index, well, we think the slope is plus 0.41, but we're 95% confident that it's between 0.12 and 0.70. So then you say, well, that's a confidence interval. What about a hypothesis test? Well, for a hypothesis test, the usual thing we want to test is whether the true underlying slope, the beta 1, is equal to 0 versus the alternative that it's some other value. Well, remember what we know. We know that if you take the observed B1 minus the true value beta 1 and divide by that crazy standard error for B1, that has approximately a t-distribution with n minus 2 degrees of freedom. And we already know that in this case, the B1 was plus 0.41, and what we just worked out was that that standard error of B1 from that crazy formula was equal to 0.148. So now we know how to compute a p-value too. It's our same old trick of starting by saying, well, what's the probability under H0 that the true value beta 1 differs from the observed value B1 in absolute value by at least what we got, which was 0.41. Well, you just divide both sides by that standard error, which in this case is divide both sides by 0.148. And then what we say is, well, that left-hand side, that's now like the absolute value of a t-distribution with n minus 2, or 398 degrees of freedom. And the right-hand side, that works out to 2.77. And it turns out that the probability, according to the computer, that a t-distribution with 398 degrees of freedom will be bigger than or equal to 2.77 in absolute value is about 0.0059. Now that's quite a small value, quite a small p-value. So probably we would have a significance level that would be such that we would reject H0. We would say it's not true that beta 1 equals 0. So in this example with the skeletons, we would conclude and say, no, there really is some sort of linear relationship, and the true theoretical underlying value of the slope is just not equal to 0. Now, you should be careful when you do either a confidence interval or a hypothesis test that you don't overstep your bounds and say, well, that means that when the BMI goes up, that causes a change in the age difference. Because after all, this was not a randomized experiment. We just got some observational data. And so that means we can't conclude any causal relationship. We can just say there's some sort of a relationship, and indeed some sort of a linear relationship, between the BMI and the age difference for those skeletons. So now let's consider a few other quick, simple examples to give us an idea of some of the limitations of linear regression. For our first example, consider the data here. You can probably tell that y has a very close relationship with x, in fact, a quadratic relationship. In fact, y is just equal to x squared here. But suppose we try to do a linear regression. Well, the line of best fit, according to the formulas, would look just like this. So it's doing its best to try to fit all these different data points, but it's not really telling us much. It's a flat line. It's saying that the slope is equal to 0, which is kind of like saying there's no linear relationship in this case between the y values and the x values. And yet we know there's still a very strong relationship. It's just quadratic. So linear regression by itself is not enough to tell us about the relationship in this case. For a second example, let's look at 4 different sets of data. In each case, there's 11 different points, 11 different x's and 11 different corresponding y's. And this is a famous example that tells us 4 different graphs. And in each one, you might say, well, what's the line of best fit or linear regression going to look like? Now, these 4 different sets of data look pretty different. One of them looks like a nice linear relationship. One of them looks like a curve. One of them looks like most points on a line, but one of them way up. One of them looks like all the points kind of squished on top of each other, except one way off in the corner. And yet, if we look at the line of best fit, it's exactly the same in each of these 4 cases. Furthermore, the mean of x is the same in each of these 4 cases, and the mean of y is the same in each of these 4 cases. And furthermore, the correlation between x and y is the same in each of these 4 cases. So this is a classic example to say, even if you know the means and the variances and the correlations and the lines of best fit, you still don't really know everything about the data and about the relationship between it. And sometimes you just have to graph it and look at it and think about it. For one final example, let's look at this set of 5 points, so 5 x values with 5 corresponding y values. And this looks like a pretty good relationship, pretty linear relationship. And indeed, if we graph a line of best fit, it goes pretty close to the data points, kind of like this. Suppose now we add one more point, a 6th point, down in the right corner like this. Well, we haven't changed the data that much, we've just added one new point, and yet if we look at the line of best fit now, then it's the purple line instead of the red line. And it's quite different, and this is a way of telling us that linear regression is not particularly robust or resistant to outliers. And if you put in just one or a few points which are very different, that could change rather significantly the line of best fit and thus the slope and the perceived linear relationship. So whenever you're studying linear regression, you should always keep in mind that maybe there's just a few outliers or a few unusual values which are skewing your sense of what the true relationship is. So now we understand a bit about how to do confidence intervals and hypothesis tests for these slopes with these linear regressions, and also some cautionary examples to let us think that linear regression is a very useful tool, but it doesn't tell us the whole story, and it's always good to do some graphs and think about what's going on and think about the limitations of linear regression.